you cannot see very detailed. The organized structure, it covers the multi-hazard, multi-element.
Pertenece a la Universidad de Twente de Holanda. Sí quiero compartir la presentación, no sé si me lo permiten. Quiero compartir el resumen del profesor, por favor. Muchas gracias. El profesor Kees van Westen, como les digo, es profesor de la Universidad de Twente, Holanda, el Instituto de Ciencias de la Tierra, que en algún momento lo conocíamos. Y cabe destacar que Kees ha estado en nuestro país y va a formar parte de los profesores de la Maestría de Ciencias de la Tierra. Voy a permitirme leer parte del resumen del profesor, ya que es muy extenso, en realidad me llevaría mucho más del tiempo que tenemos planificado. El profesor Kees van Westen received his Master Science in Physical Geography from the University of Amsterdam in 1987, and his PhD in Engineering Geology from the University of Delft in 1993. He is expert on multi-hazard risk assessment in mountainous environments. He has carried out research on different hazards and risk-related aspects, landslide hazards and risks, volcanic hazard and risks, and earthquake-induced hazard in different regions, like European Alps, Central America, South America, Caribbean, Caucasus, Central Asia, Himalayas, China, India, and Indonesia. He worked on national-scale multi-hazard risk assessment project in Central America, Caribbean, the Caucasus, Central Asia, and Pakistan. Kees was involved in numerous ambassador and capacity building projects, supervises more than 110 master science students and 20 PhD researchers. He publishes over 125 scientific papers. His current research interest is to develop methods for the analysis of changing multi-hazard risks. These changes can be abrupt, example, after major disaster, like earthquakes, tropical storms, volcanic eruption, or gradual, analyzing how future scenarios or climate change, land use change, and population change have an impact on risk, or a decision or support tool for the planning of risk reduction measures. Aprovechamos la oportunidad justamente para dar gracias a Kees por estar el día de hoy y compartirnos parte de su gran experiencia. Kees es un referente no solamente en Holanda, los Países Bajos, sino también en Europa. Thank you very much, Kees. The audience of the screen is yours.
Muchas gracias. Entonces voy a compartir pantalla. ¿Está visible?
Sí, Kees.
Sí, ok, muy bien. Entonces, muchas gracias para su invitación a ese evento muy interesante y mis felicitaciones para el establecimiento del centro con respecto a estudios de riesgo en ESPE. Si me permite, voy a hacer mi presentación en inglés. Para mí es cambiar rápidamente a español, es un poco difícil porque en ese momento, durante el tiempo de corona, no estuvo en Latinoamérica. Entonces, para mí, hablar en inglés sería un poco más fácil. Okay, so moving to English, I would like to present, as was asked by the organizers, to present some work that I had done on the analysis of landslide risk in relation to risk reduction planning. I think the title was a bit more restricted to hazards, but I would like to broaden it a bit more also towards risk, and also see how landslide risk as a component of multi-hazard risk still is one of the major challenges, I would say. I have been also indeed to Ecuador, but have not done extensive studies in Ecuador on landslides. but I'm following the landslide blog from Dave Petley, one of the most informative sources of information with respect to landslides, where he reports landslide events from all over the world and also gives background of that. And while looking at that landslides blog, some of the clear evidences of landslide problems in Ecuador also came up. Here are a few of the examples that I was able to find. Upper right, one example that has a large economic consequences of relatively small landslides that happen along major oil pipelines in the Ecuadorian area and along the Coca River, making ruptures of these oil pipelines and producing huge amount of pollution and also a loss of oil. And so the area was, the following day, the Ecuadorian government declared force majeure, and say around 4,000 barrels were actually polluting the area. The left example is another typical example of what we would say multi-hazard problems with relation to landslides. Here, a major event that happened along the Coca River in July 2020, when a huge valley blocking landslide blocked the river, causing temporary lake. And in the upper images, you see how the lake is, how the dam is broken and resulted in a dam break flood event. Another example here, a most recent one from this year, I think all of us have seen that very spectacular and large event that happened in Twente, this huge landslide that was forming really like a liquefaction type of behavior, very rapid flow type of phenomena, affecting quite a lot of areas with quite some damage. The point here, all of these examples illustrate the difficulty actually of dealing with landslides as a damaging phenomena, especially when we are also looking at, say, the risk assessment of those, being the probability of losses and also the interactions between the different events. So how could we, say, take these kind of phenomena into account in preventive planning? This is still a major challenge, I would say. So when we're looking at risk and we look at multi-hazard risk, we are considering a probability of losses of a certain type, and we look at the different individual risk components. I'm sure that others have already addressed this problem, this point in earlier talks, but where multi-hazard risk assessment definitely deals with multiple hazards, multiple event probabilities, multiple assets, and multiple loss components. And especially when we're looking at, say, landslides, we would say that the landslides are by definition multi-hazard events. They're different, they have different triggering mechanisms, could be as a result of earthquakes, could be extreme rainfall events, but can also be associated with mining activities or with other human interference. And so they are actually a container term of many different processes that all present also different type of intensities. So even a single form of intensity is not possible for landslides. And they have also many interactions. So landslides would interact with drainage, with discharge to form, for example, debris flows. And you would also say that to some extent landslides are what you call a random phenomena. They would be much more difficult to predict in terms of its location than other hazardous events, say flooding that is located on very clear areas where the magnitude frequency relation is there, the issue. with landslides, the locational aspect is also the big problem. And so there's a lot of issues involved that make that landslide risk assessment is still one of the major challenges with respect to quantifying the risk of them. And so we would be looking in this presentation a bit more towards these components. I would first have a look at, say, the hazard component, and later also towards the risk component. So within the hazard component, we would need to have information on the type of event that would happen, their interaction, the frequency, and if possible, intensity information. But in a lot of cases for landslides, this would not be possible. So we would not be able to make a map of frequency intensities, and we would actually have to deal with more simplified way of susceptibility and then representing the likelihood of occurrence as a spatial probability of occurrence as an attribute of the susceptibility classes. So this also makes that, for example, application of vulnerability curves within the risk assessment is much more complicated, as landslides often do not portray a clear intensity relationship, and therefore also in terms of quantitative risk, it is a difficulty. So we base ourselves within landslide studies very much on known events. So if we have no historical landslide inventories, it's very hard to make good and sound predictions of where these would be happening and also what would be the risk associated. So there's a lot of effort being done on establishing better landslide inventories. And nowadays we have a large array of methods available that would allow us to do this. And they range from traditional field mapping approaches, but where the scale, of course, also very relevant, going towards participatory approaches, but also in some instances to smart sensor networks where, say, for example, soil moisture or movements are being measured by small devices that are in a network. Crowdsourcing definitely is one of the main upcoming tools where it is less successful, I would say, for landslides as it would be for the mapping of elements at risk, where tools like OpenStreetMap are, of course, the main tool where crowdsourcing is actually being used to collect information. Although we have, say, tools like the Landslide Reporter by the NASA, it's not being used very frequently. So a lot of the data would have to be derived by specific surveys often. And so there, remote sensing plays a very dominant role, and from all different scales of analysis. It could go from measuring displacements using INSAR to automatic mapping of phenomena using deep learning methods, machine learning methods, now also through much more automated techniques following, say, freely available data like Sentinel images available and Google Earth Engine for doing this in the cloud. Also, special dedicated cloud servers for landslide mapping have been developed. For example, tools under the GEP GeoHazard platform, under Copernicus program for the ESA. And there are also more satellite images available to do this work. As for example, the Planet Lab constellation of images that provide us images also almost on a daily basis. So this availability of images has been increased, and also the capacity to automatically extract inventories from it. But the sharing of those is still a big problem, I would say. So there have also been attempts to better share landslide inventories. A good example of that is the sharing of earthquake-induced landslide inventories. In order to advance further in the study of earthquake-induced landslides, we need to develop statistical relationships between the causal factors, like terrain factors, geology factors, seismic factors, and we need to do that for a wide range of different events. So having a database of inventories is of large importance. And so there's still, there are now more and more becoming available, but it's also important that these are shared among researchers. And here's an example of a worldwide database of earthquake-induced landslide inventories, which is hosted by USGS and which also is regularly updated, and where anybody can access the inventories, but also contribute with new inventories. For rainfall-induced landslide inventories, there is also a lot of activity going on, mostly supported by the NASA landslide program in collaboration with an international research group around what we call Land Aware, that also focuses towards, say, landslide early warning. And one of the aims there is also to collect many rainfall-induced landslide inventories and bring them together. The number of these events already have been developed. There are still many challenges there in terms of mapping them properly. There are many of the inventories have big issues with respect to their completeness, also with respect to the spatial accuracy and the attribute accuracy, and also with respect to the detail with which they have been mapped. And so, for example, in terms of the size frequency distribution of, say, what is the expected size of landslides given a certain event, this is very relevant. Also, the temporal frequency. So in this middle, you see an example of a multi-temporal inventory showing how landslide activity changes after a major event. So would like to show you one example in particular of work that we did after Hurricane Maria, 2017. That was a major tropical storm, a hurricane that category 5 went straight over the island, Caribbean island of Dominica, causing about 10,000 landslides. With the help of UNOSAT, UNITAR, we mapped the events, the landslides and the debris flows and the floods in detail for this particular event. We used that information together with other events that have taken place before on the island. So we collaborated with other researchers on reconstructing landslide inventories for past events. So we have here one from 1987, from 1990, for another tropical storm for 2014, a recent tropical storm 2015, and then the major event of 2017. Having multi-temporal inventories available for a certain area allows us to much better establish these frequency density distributions of landslides within terrain units using statistical methods. Here, an example of such a resulting landslide map where the units themselves are geomorphological units, and say the legends are based on, say, the frequency and density distribution of events that could happen over time. So based on these multi-temporal landslide inventories. So establishing good inventories is extremely important for such type of, for better risk assessment of landslide related phenomena. Another recent example I could give is from Kerala in India, the southern tip of India. It's one of the more mountainous parts of India, except for the Himalayas. This is a region which is bordered by the Western Ghats, a very mountainous, hilly region. which also suffers a lot of landslide problems. We also looked at this area after the 2018 monsoon, which was extremely heavy in this area and which caused also a huge number of landslides, making a lot of damage. Here in the picture, you see an example of a secondary school complex, which was destroyed by a major landslide in this event. One of the issues within this area was that there was always mentioning about, say, the large relationship between land use changes and landslides that have happened. So this was one of the reasons why we, together with the Kerala State Disaster Management Agency and with support from UNEP, UN Development, set up a study on analyzing whether these recent events, these landslide events, were actually having a relationship with recent land use within the area. So for that, we collected landslide information from different sources, and we corroborated all of the landslides using visual image interpretation with a team of people. And the visual image interpretation was carried out based on Google Earth images. The original source of data came from two main sources. One was the Geological Survey of India, who only collected information from the landslides that actually created damage. So out of those landslides, a subset, they had a very strong relationship with recent land use changes, as a lot of them were, for example, related to building cuts or road cuts. The other database that we used was landslide information from remote sensing data using automated assessments. So what we did was merge those information together, check also with, say, carefully with Google Earth images, what was this, whether it was a landslide and what was the land use change in the period 10 years before. And so based on that, we made kind of a new inventory of about 4,000 landslides by, say, using a number of those derived from the automated machine learning based method, and also integrating the ones from the field. And we'd be able to make a much better assessment of the relationship between land use and landslides within this area. As I mentioned before, the landslides are a container term of, say, in the multi-hazard interactions. And so they could be grouped also with respect to when we do this in risk assessment in different hazard interactions. So they could be independent events, so events that are not related to each other, and where also within the risk assessment, we could actually treat those completely independent. They could be compounding, so that would be two independent events that happen at the same time, but because they happen close to each other, the impact that they would have together is much higher than if they would be looked at individually. So one of the types of events we often look at are coupled events, so events linked to the same trigger. Say, for example, events linked to a tropical storm, wind, rainfall, extreme rainfall causing flooding, but also landslides, as well as storm surge events that would affect partially the same type of elements at risk. The much more complicated one to analyze are the domino or cascading hazards, where one triggers the next. And so where this might be very difficult to represent spatially in the case of landslides, for example, earthquakes triggering landslides that might block rivers. And the last, in hazard relation, what we would consider would be conditional events. So those would be events that change the condition of, that make the landscape much more susceptible for other types of hazards. So a good example of that is an area affected by forest fires, which then becomes much more susceptible by landslides. So in that case, the landslide risk would increase substantially after a fire event. So these taking these interactions into account is extremely complicated, I would say, within the landslide field. Like we saw initially also in the example from Ecuador that landslides have also an effect on the downstream part, for example, by blocking rivers. Here also an example, but this case from China after Wenchuan earthquake 2008, where we did a lot of work, where there were a lot of landslides blocking rivers or debris flows that happened after the landslide, after the earthquake, several years after, that also blocked the rivers, and that caused flooding. And where we tried to apply multi-hazard models to model these events. So write an example of a large event where we use the flood model to also model what would be the flood height and the reach time to reach to a certain city downstream of this. So normally we apply these type of multi-hazard models by linking individual models together, but this is very complicated because the output of one model is the input of another, but very often the processes are completely interacting. So this is also one of the reasons why we have developed called a multi-hazard model. It's called OpenLISAM. It's an example because there are several others developed around the world. This is, I think, one of the important new developments where you're trying to model all the processes that happen during an extreme rainfall event and also how they interact with each other. So there could be, say, slope stability, rainfall runoff, erosion, sediment transportation, but also debris flows or flash floods. And so depending on the characteristics, either one or more of these events could happen at the same time. So this also is one of the areas where we tested it in the same area in Dominica after the Hurricane Maria. Here you see the image of an example of the southern part of the country before the major hurricane. It's very forested areas you see, and here you see one of the villages completely hidden within the forest. And after the event, the whole area is basically got rid of vegetation because of a huge amount of, say, very strong winds and very severe landslide activities. So the change between those two events is enormous. And say the density of landslides within the area surrounding that village was also enormous. So one of the aims of this multi-hazard model is also trying to model the initiation of landslides. But that's quite a challenge because it very much depends on, say, input factors like slope thickness and the geotechnical characteristics, which are more difficult to represent spatially. On the other hand, say, the volume of materials that they would deliver are much more better in control. So the actual location of landslides, as you would see, differs still quite a bit from the modeled and the actual observed ones. But the resulting flows can be better modeled. So here, another example of the application that we use with this model, and while it's running on the left side and kind of an animation, we model, say, the combination of sediments as well as water. And so the resulting flow is then indicated with colors indicating flow height as well as solid content. And so this allows us to better model, say, the change from flooding to debris flows. We did this work also for a World Bank project in the country, where it was also important to look at the behavior of bridges. And so we calculated also the peak discharge at the bridges, but also the sediment amounts. and also the behavior of tree logs. So a huge amount of tree logs got eroded and involved in the movements, and they also damaged a lot the areas. So another example of a multi-hazard component. And finally, we also looked at, say, sedimentation. So because of the huge volumes of sediments, after the event, a large amount of sediment remains, lifting up the riverbeds quite significantly and making the areas much more susceptible for flooding in the next event. So these areas would have to be cleaned, have to be dredged, and for that also the modeling of the volumes of sediments is important. So we did both an attempt to do this with the modeling and also verified it using measurements of sediment depositions using UAVs and LiDAR data. So having this information then requires us to do the risk assessment. Then we have to make a selection which of the various tools we could apply in applying, say, a risk assessment for incorporating these multi-hazard landslide components. And sometimes that would be a more qualitative approach, and other cases more semi-quantitative, and in other cases when we have better information, it would go to quantitative. Very often it would not be possible to do a full probabilistic analysis, but often we do a kind of semi-probabilistic where we're looking at different return periods in relation to its susceptibility maps and spatial probability information. So one example of such multi-hazard studies was work that we did in Tajikistan, in Central Asia, where we developed risk profiles for the country for 7 types of hazards and 4 types of elements at risk, and also developed it into a web portal where users can generate their own risk profile for the own area of interest. So these were for all the area, multi-hazard maps were generated, which were classified in simplified classes, and a loss estimation procedure was done where we calculated exposure, then integrated it with vulnerability, then calculate the loss for individual hazards and return periods, and then bring those together in a multi-hazard risk analysis. Then the end users could see that information and make selection of what kind of information they would like to see in terms of combination of assets, elements at risk, and hazards, and generate their own risk profile for a municipality or a district. We also use this information, the multi-hazard risk information, in a decision support kind of tool where we would support decision making on which risk reduction alternatives could be employed by analyzing first the current level of risk, then looking at future trends, so in terms of climate change or land use change, then considering different risk reduction alternatives, and see also how they behave in together. An example of that is shown here for an area in Colombia, in the city of Medellin area, city of Envigado, which is affected by both flooding and debris flows, where we developed an example of analyzing first the present multi-hazard, then look at possible future scenarios in terms of climate change and urban growth, and then evaluated different risk reduction alternatives and see how they behaved under these scenarios. So this is an example of, say, the risk assessment approach by doing first a multi-hazard modeling, where we can derive here intensity maps of flooding and debris flow for different return periods. We characterize the buildings in terms of elements at risk and characterize them with their physical vulnerability curves, and then run it through a risk calculation tool to do the risk quantification to get the average annual loss per year for the current situation. And then we tested, say, different scenarios, future scenarios in terms of population growth, as well as climate change, and say analyze the same type of combination of factors, but then with different hazard maps and different element at risk maps and vulnerability curves for future scenarios to see how the risk would change over time. The risk would also be very different in terms of which parts of the city. So this would be also analyzed, whether they would be more in the residential areas or not. And then we analyzed what would be the optimal risk reduction alternatives. So whether more, say, hazard reduction related alternatives would be better, or also much more vulnerability reduction alternatives. And so we could see how they would behave then under these different future scenarios.
Okay,
so this way,
we have 5 more minutes.
Yes, I am almost ready. Yeah. So this requires that we use these kind of tools to do this. Unfortunately, many of the tools that are, say, may not be that suitable to incorporate landslides within this whole procedure. And they have various reasons. They're not supported anymore. They are one specific for one type of hazard. So given that, we are actually busy developing our own risk assessment tool that analyzes how risk changes over time. It's called also Risk Changes. We develop it together with the Asian Institute of Technology. And the idea is that we are that this tool allows to calculate multi-hazard risk for the current situation and for different alternatives, and how these change also over time. It has a cost-benefit component and a multi-criteria component. So this is now under development. It's based as a series of Python scripts, and we also have it as a graphical user interface available through riskchanges.org, and we are further expanding that in the coming period. So with that, I would like to thank all the students and fellow workers that have been working with me on all the different examples that were shown. Also, I would like to thank you for your attention, and happy to answer any further questions. Thank you very much.
Cees, muchas gracias. Gracias infinitas por tu presentación. Es muy poco tiempo para poder mostrar toda la experiencia y conocimiento que tiene el profesor. Voy a hacer un resumen muy rápido de lo que el profesor nos ha mostrado el día de hoy. Sin dejar de mencionar antes, ¿no? Sin dejar de mencionar que en la universidad hemos trabajado mucho en el tema de deslizamientos. Uno de los participantes que están asistiendo indican que es una charla pertinente y relevante. Todos los comentarios son de una gran exposición que se ha mostrado el día de hoy, pero como decimos, pertinente y relevante. En nuestro país hemos tenido eventos de este tipo muy grandes, como alguno que ya olvidamos, el de la Josefina, que ocurrió hace muchísimos años, y el profesor Cees nos mostraba ahora mismo lo que está sucediendo ahora en nuestra Amazonía, y en Chunchi, un evento que ocurrió en este año, un evento que nuestros investigadores al momento están investigando y tratando de determinar las causas de por qué se está produciendo y posiblemente evitar una desgracia mayor. Un evento que posiblemente no lo tomamos en cuenta por la lejanía que se encuentra, y al momento estamos pensando en un evento mucho más grande como lo que es en Coca. El profesor mostró muchas herramientas nuevas que estamos utilizando al momento. Por ejemplo, la tecnología de radar, INSAR, metodología muy interesante como Machine Learning, LiDAR o LIDAR, utilizado conjuntamente con datos de UAV, una tecnología que está muy difundida al momento, pero que posiblemente no se la está explotando al máximo. Información de plataformas satelitales como Sentinel, Copernicus, y un tema muy interesante, habló de cartografía colaborativa, el uso de OpenStreetMap, de Google Maps, y estas herramientas, cómo se pueden integrar con sistemas de información geográficas fuertes como el ArcGIS. También nos habló de todo lo que es el análisis multitemporal, una herramienta muy interesante, cómo va cambiando los eventos y cómo pueden producirse, justamente para ver qué puede pasar en un determinado futuro. Habló y nos mostró modeladores de deslizamientos y modeladores, por ejemplo, inclusive para cálculo de volúmenes en sedimentación. Y un tema muy interesante, el multihazard o el análisis de multirriesgos, inclusive cómo puede integrarse a lo que es cambio climático. Todo está orientado a lo que es toma de decisiones y pensar qué es lo que tenemos a futuro. Un resumen muy rápido que es, y tenemos un par de preguntas interesantes, ¿no? Nos dicen, voy a decírtela en español y en inglés, si es que prefieres.
Bueno, lo podríamos hacer en español, sí, no hay problema.
Bien. Nos piden ampliar un poco el tema de cómo la actividad humana incrementa el riesgo de los deslizamientos, particularmente en nuestros países, en donde justamente tenemos un problema en la parte del manejo de asentamientos de población, asentamiento de diferentes actividades de tipo antrópico.
Sí, gracias. Bueno, hay muchas maneras en donde la actividad humana afecta mucho a amenaza por deslizamientos, pero lo más común es cortes artificiales no controlados. Por ejemplo, en muchos de los casos también que en el caso de la India, la mayoría de los deslizamientos que han causado daños fueron por cortes de edificios. Entonces, cortes sin ningún tratamiento o también cortes en carreteras, pero también cambios en vegetación, aunque no siempre era simple de deforestación causa deslizamientos. En general es así, pero el ejemplo también de India nos demostró que muchos de los deslizamientos que ocurrieron eran en áreas de bosques. Entonces, durante grandes eventos, ese también puede ocurrir, pero cambios de uso de la tierra, de todas maneras, contribuyen mucho a la ocurrencia de deslizamientos. Entonces, esos son algunos de los ejemplos de que como el factor antrópico puede ser importante, es supremamente importante.
Gracias, Cees. Justamente la actividad humana posiblemente no se la toma en cuenta cuando no se tiene un desarrollo orientado o ajustado a lo que es un ordenamiento territorial, como tú lo dices, cambia el uso de suelo y no necesariamente es el adecuado. Y ahí vienen los problemas que se vienen a dar. Un ejemplo muy claro, el que mostraste inicialmente, el de Chunchi, alguna actividad que no necesariamente es la adecuada, llegó y provocó ese evento. Actualmente en nuestro país estamos saliendo de una época invernal, ¿no? Y en la cual hemos tenido muchos eventos de este tipo, pero que no necesariamente provocados por, muchas personas piensan que son los eventos meteorológicos que los ocasionan, pero no se dan cuenta que en realidad son esas actividades que posiblemente son las que llevan a que se incremente esa posibilidad de producción de este evento. Nos preguntan, ¿cuáles son los principales impactos observados de este tipo de evento en países en vías de desarrollo? Estamos hablando países como nuestros, del Ecuador, una realidad muy diferente a lo que son países en Europa o en otras dimensiones. ¿Cuáles son ese tipo de impactos? Nos mostraste justamente algunas herramientas para evaluación de esos impactos, inclusive hablaste de diferentes tipos de vulnerabilidades, cómo se pueden relacionar ambas ¿Y cuáles son esos impactos que se ha observado o que tú has podido medir en nuestros países?
Sí, creo que hay una diferencia entre los impactos entre países en desarrollo y países como en Europa, por ejemplo, en donde el impacto con respecto a vidas humanos es mucho más grande en áreas en desarrollo, especialmente por parte de planificación inadecuada y la localización de muchos áreas de construido sobre laderas no apropiado para esto. Entonces se generan problemas de deslizamientos. Son causados por los actividades humanas, pero también impactan directamente a los asentamientos humanos. Entonces el impacto de vidas y de viviendas es muy grande y como que también es muy importante impacto en redes de transporte, en redes, por ejemplo, redes de oleoductos, como hemos visto en el ejemplo, que generan también impactos indirectos muy grandes. Entonces, como interrumpen transportes o generan polución en el caso de rompe de oleoductos. Entonces, estos impactos son mucho más difíciles de evaluar porque requiere también mucho más información sobre aspectos sociales y económicos para evaluar esos tipos de impactos. Con respecto a vulnerabilidad, naturalmente tenemos que ver la vulnerabilidad físico como directo impacto, pero igualmente importantes son las vulnerabilidades que no se puede captar directamente en curvas de vulnerabilidad, como vulnerabilidad social humana y la vulnerabilidad ambiental. Y lo que ahora es muy importante también en la comunidad europea, tenemos el próximo programa de investigación en donde se toma mucho énfasis en vulnerabilidad sistémica. Entonces la vulnerabilidad del conjunto de la sociedad y cómo impacto de amenazas afectan, de desastres, afectan todos estos sectores y de la sociedad. Entonces se va mucho más lejos que simplemente un impacto o vulnerabilidad físico. Y este sí es una de las áreas en donde hay mucha investigación requerido en todo el mundo. Gracias.
Muchas gracias, Cees. Muchísimas gracias también porque hemos cumplido exactamente con el tiempo, una puntualidad, como solo nuestros profesores holandeses la tienen exactamente dentro de el minuto que habíamos planificado. Esperamos que es poder hacer quizás el próximo año de nuevo aquí en nuestro país y que sea igual de placentero tenerte aquí y que tu viaje no sea tan accidentado como el último, pero que...
Sí, el ojo está funcionando.
Qué bueno, qué bueno. Esperamos tenerte acá y poder contar con tus experiencias, con tus conocimientos. Como digo, agradecemos siempre el poder aprender algo nuevo y creo que con tu charla todos, inclusive algunos que conocemos un poco de este tema, hemos aprendido mucho el día de hoy. Muchas gracias a la audiencia, muchas gracias, Cees. Gracias y doy la palabra a los organizadores para continuar con el evento.
Gracias, mucha suerte.
Muchas gracias, Cees, de corazón. Thank you very much, Cees. Really, very, very good presentation and also very motivational. I think, you know, all of us, we are starting something new and we need the support of people like you, friends like you, that not only with the knowledge, but also, you know, with experience and the encouragement to start something that is not easy, you know.
Yeah.
any
Oh, I
place
can
in the world
imagine.
is difficult. So we count on people like you to move ahead. And so thank you very much.
Carlos, you are now also in Ecuador then? You are working?
No, I'm in Hawaii now.
Oh, in Hawaii. Okay.
Yeah, I live here for the last 3 years or so.
Much better.
Come and visit.
Todos vamos a ir, Carlos.
Ya, no hay problema. El centro se hace aquí, el de Ecuador. Good.
Ok, bueno, muchas gracias.
Gracias.
Cuente con el resto del taller.